All right, so the great debate, who invented calculus? What we're going to look at today is Leibniz notation. Leibniz, don't really know how to say it, but yeah, it's between Newton and this guy Leibniz for who invented calculus first. Newton, I think, generally gets the credit, but it's apparently Leibniz had sort of worked on it in his notes before it sort of became public. Anyway, so let's see what we can make sense of. So if we look at this function f of x in green, you see I've got this square here. So what we're going to do is we're going to zoom into that area and think about a few things that are going on. So you can clearly see, firstly, that there's a bit of a curve to this graph. But as we zoom in, when you zoom in to a function close enough, generally it looks pretty linear. It looks like a straight line, right? So we sort of get something that might look like this if we zoomed in. And what we're going to talk about today is obviously Leibniz notation and how important it is because we're going to use it when we're solving differential equations in a little bit. But in any case, it's good to know it anyway. So let's imagine we take some point on this function f of x and we call that point x, xy. All right, and then what we're going to do is we're going to take a little distance that we're going to call dx to the right of that. It could be to the left, but we're going to do this to the right. So some distance dx from x, right? So then what we get is we go up from there, and then we get the distance dy. So that's the small distance y that we've traveled, right? And then what we can do is we can make a little triangle out of it, and then we get this new point must be at, or must have an x coordinate of x plus dx. It's been moved to the right by dx. And it must have a y coordinate of y plus dy, right? All right. And what you may have noticed in previous videos is that we actually had a definition of the limit. Definition of the limit is that f dash of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. But this h idea is actually nothing more than this dx idea, right? In fact, I don't really know why we use h. I feel like it could potentially be more intuitive to use dx. In any case, here's what Leibniz's notation says. It says, all right, well, we can just define the derivative f dash of x as dy over dx. The change, the rate, the ratio of the small change in y divided by the small change in x will give you an approximation, a very good approximation if dy and dx are small enough or close enough. Yeah, if they're small enough of the gradient of the graph at that point. So yeah, we just write dy dx as the limit as dx goes to 0 of f of x plus dx minus f of x all over dx. And you'll see as well, as dx gets closer, as dx gets smaller, yeah, we're taking dx approaching 0. So this is a very handy way to be able to express the derivative of a function as dy dx. But I suppose the big idea that I sort of want to get across here is that we can actually think about it as a fraction in a lot of ways. It literally is the rate, it literally is this distance divided by this distance, which is a fraction, right? And when we're going to solve some more tricky problems later on, it's going to be important to know that we can sometimes treat this as a fraction. And this is by no means super in depth, but yeah, I just wanted to give you the intuition for why you might be able to sort of treat it as a fraction. All right, good stuff. Keep up the hard work.